In 2001, Marcus Raichle and colleagues pointed out something that everybody had been ignoring for years. When you put someone in a scanner and give them a task, certain regions go up. Fine. That is what everyone was studying, but a different set of regions consistently went down the moment the task started, and back up again when the person was left alone to lie there and think about nothing in particular. Those regions were more active during tests than during work, which is a strange thing for a brain to do, and for a while people treated it as an artifact. It's now called the default mode network. I've been mentioning throughout the sessions that the default mode network, aka the DMN, is the celebrity of the brain networks. So now we know why. It is one of the most studied systems in the human neuroscience, and it is involved in remembering, imagining the future, and thinking about other people's minds. Today we're going to measure it in 50 real people and test whether it changes as those people grow up. Okay, same dataset as last session, same atlas, same masker, but 50 participants this time, 25 children and 25 adults. Extracting 50 people takes a few minutes, so it is done once and cached in the repository. The script that built it is in there too, so nothing here is a black box. Let's acquire data first. And then let's load. Okay, so participants, time points, regions, a three-dimensional array, and the age range tells you something important that we will come back to at the end. Okay. Session 10, 50 times over. So basically this box of code you see is session 10 but 50 times. One line for each participant. Transpose their arrays so regions are on the rows, then correlate everything against everything. 50 matrices, 39 by 39. Now let's visualize everything, because I think that's the best way to actually get an idea. Okay, children on the left and adults on the right, averaged within each group. Both show block structure, which is the modular organization we built by hand in session 10, now emerging out of real brains without anybody arranging anything. And the adult matrix looks a bit more contrasted. Now, looks a bit more is not a finding. That is exactly the kind of impression that turns into a wrong claim if you let it. So let's measure it properly. Let's have a hypothesis to actually study. Here is a hypothesis, and I'm starting it before running anything. Setting it actually. The default mode network becomes more internally coordinated between childhood and adulthood. This is not something I invented. It comes out of developmental imaging work from around 2008 onward. And the general pattern is that as brains mature, networks that are scattered and locally organized in children become more integrated across distance. I actually, one of the studies that I actually conducted on a sort of database that I will actually go into the details after it is published, so I don't want to give out anything. Basically, it was that for the first time, without actually looking at other papers that has studied this phenomenon, I actually observed the same hypothesis on a longitudinal dataset, fMRI dataset, and this is amazing. So, our atlas has 4 default mode regions. For each participant, we take the average correlation among those 4, which gives one number per person. One number, one question chosen before looking. That is the difference between a test and a fishing trip. After all, we are trying to be, actually, at least look like a scientist. And after session 9, you know exactly why that matters. Now let's run our codes. So the four type of the four default mode networks I mentioned: the LDMN, medium DMN, frontal DMN, and the right. Okay, now there it is. Now you can actually go and study it statistically. Adults show stronger within network default mode within network default mode connectivity than children. Look at the p-value. Is small, and the effect size, more importantly, is large. You don't usually go on and see a Cohen's d value of an effect size value of 1.06, specifically in this field of study. So and I want to point out that we report both, because a p-value on its own would not tell you whether this is a big deal or a tiny difference measured well. You just reproduced a real developmental finding and on open data in 15 lines of code on a laptop, probably, but I'm on a laptop. Let's visualize the finding. Okay. Left panel, two groups. Right panel, same thing, plotted against age as a continuous variable. Now look properly at the right panel, because there is a lesson sitting in it. Age is not two groups, it's a number, and our sample is a cluster of young children. A large empty gap, as you can observe right here, and a handful of adults at the far right here. That straight line is doing a great deal of guessing about the middle we have almost no data for. Splitting continuous variable into two groups always throws information away, and it can create appearance of a step change where the reality is a smooth gradual one. Sometimes this split is a fair simplification. It is your job to say out loud that you have actually made it. So, the caveat: I'm not going to skip. There's a confound in what we just did, and it would be dishonest of me to end the course without naming it. Children move more in the scanner than adults. That is not a small effect, it is one of the most reliable facts in developmental neuroimaging and head motion changes measured connectivity. We regressed out motion-related confounds during extraction, so we did something about it, but confound regression is a partial fix, not a solution. And the field has spent more than a decade arguing about how much of the apparent developmental changes in connectivity is maturation and how much is children wriggling. The finding here is real and it replicates, but a proper version of this analysis would check whether motion differs between our groups and whether the effect survives controlling for it more aggressively. I'm telling you this because it is the difference between running an analysis and understanding one. The scientific way, the honest way. Every result has a next question, and it is usually about a confound you did not measure. Now let's get to the network view, my favorite class to look at neuroimaging data. Last thing, session 10 again. On the group averages, same threshold, same layout, same regions, so the two pictures are directly comparable. The adult network carries more edges. 31, right? 43 against 31 in children. That is the same group. And the threshold caveat from session 10 applies. Change that number and both pictures change. So actually we are showing one slice through a decision. Let's run the plotting as well so we can actually observe what I'm discussing. As I mentioned, same threshold, same layout, same regions, but the difference in thresholds is actually something that you should understand. Now look at this beautiful image. The modularity in adults starts to actually be more sensible, even just looking with your bare eyes. You can see that the modularity is somewhat happening. 12 sessions ago you wrote firing rates gets 12.5. Since then, you have written functions, handled real data structures, built and filtered a signal, tested the hypotheses, learned what a p-value does and does not say, turned the correlation matrix into a graph, and downloaded a public neuroimaging dataset that you reduced with a brain atlas and analyzed across 50 people. Nothing in these last two sessions used a tool that you had not seen or already met. That was the design. Session 11 and session 12 are not harder than session 5, they just point out something real. Packages worth your time. NE, Python for EEG and MEG, and the tutorials are genuinely excellent. Nelearn for fMRI, which you have actually used in this course. Nibabble or Nibabble, depending on how you pronounce it, for reading file formats directly. Brain2 or Nest if you would rather simulate neurons than analyze them. Spike interface for extracellular recording. Data to practice on. OpenNeuro has thousands of datasets in a standard format. Abide and ABID and ADHD 200 are both reachable directly through Nelearn, the same way we fetched today's data. The Human Connectome project, another dataset if you want high quality data and are willing to read the documentation. And 3 habits actually that which make more than any package. Put your analysis in a version control from day one, not when it is tidy, day one. Believe me, this is based on experience. Set your random seed and write down every threshold you chose, including the ones that felt obvious. And plot the raw data before you plot the summary. That habit has saved more analyses than any statistical has ever done. That is the course. You do not need a scanner, a license, or a permission. The data is public and the tools are free, and now you can use them. But whatever you built with this, I would genuinely like to see it. Leave a comment, open an issue on the repo, send me a plot, and thanks for sticking with it to the end. Go and analyze something. Good luck.